So the first definition. Let the midpoint of the diameter of both the hyperbola and the ellipse be called the center of the section, and let the straight line drawn from the center to meet the section be called the radius of the section. So if you have some ellipse and you have a diameter and you have a midpoint of that diameter, and you draw some line from the midpoint to the section, those are radii of the section. And for a hyperbola, same thing, but the diameter is here. You have a midpoint. If you were to drop some line like this, that would be a radius. And the second definition is, and likewise, the midpoint of the transverse side of the opposite sections be called the center. So the transverse side is just another name for transverse diameter. So this is just the definition for center versus the other one was the definition for radius, but you know, same diagram, same thing. And the third definition is, and let the straight line drawn from the center parallel to an ordinate being a mean proportional to the sides of the figure and bisected by the center be called a second diameter. So if we extended this line all the way through the figure, for instance, and if this was parallel to an ordinate and a mean proportional to the sides of the figure, the sides being the transverse side, which is this diameter, and some hypothetical upright side, which we draw, and mean proportional, here, I'll draw this out. Mean proportional just means that in a ratio setup, like that as AB is to CD, CD is to AE. So mean proportional means that it's in this mean middle part of the proportion between two other things. And the sides of the figure are, again, the transverse side and the upright side. Now, usually what we're doing in previous propositions is we're defining the upright side's length. But what this is saying is that if you have a second diameter, part of the definition of the second diameter is that it's going to be mean proportional between these two sides. In an ellipse case, it seems pretty obvious that CD is going to have a definite length, right, because that length is determined by the points C and D, which are on the section, right? But, for example, if you had a hyperbola and you were going to draw a second diameter, you know, the second diameter might look like this. And it's not clear that this line would necessarily have a definite length, right? Why would it? It's not bounded by something particular, right? But even in a hyperbola, this second diameter hypothetically has endpoints, and those endpoints are determined by, you know, if this was the diameter AB, if you had an upright side AE, this was CD. CD, the length of CD would be determined by the lengths of AB and AE. So I think that definition is kind of interesting because it's sort of counterintuitive in that way. And it almost sounds when you read it as if setting up this proportion without proving that that must always be the case, especially for the hyperbola. And I think I know why it thinks that this is sort of already proven, because in Proposition 15, which was 2 propositions ago, we started with an ellipse, and we started with the diameter AB, and we constructed AE in this way, and then we proved that CD would be a conjugate diameter to AB. So I think kind of seems like to me like a converse of Proposition 15, which is not exactly Is that proven? Maybe it is. But anyway, that was kind of bothering me. So when I first read this is my second time going through Apollonius, but when I first read that, I thought it would be interesting to take the ellipse case, because in the ellipse, CD is bounded, and try to figure out whether there's some way that we can show definitively that CD must be a mean proportional between AB and AE, instead of just saying that it always works. I wrote up sort of a fanfiction proposition, and I thought it would be fun for this video to just read through it. So anyway, I call it Proposition 16.5. So given a line from the center of an ellipse, center meaning the center of the diameter, I guess, parallel to an ordinate and bisected by the center, to show that it is a mean proportional to the sides of the figure, namely the transverse diameter and the upright side. Let there be an ellipse with transverse diameter AB and center C, and let a line DE, parallel to an ordinate, be drawn through that center. Let an upright AF be drawn from A perpendicular to AB. Then let the straight line FB be joined. From the center C, let a line CG be dropped parallel to AF from C to where it intersects with the line FB. Okay, so I think basically what I just set out was those three things. Okay, I say that BA is to DE, DE is to AF, and therefore that DE is a second diameter by definition 11. So DE is the mean proportional. Okay. So DE being drawn parallel to an ordinate, it is an ordinate, so that means that the square on DC is the square on an ordinate is equal to the rectangle GC AC. So the rectangle against the upright side is equal to the square on the ordinate. So that's from 113, is that the ellipse one? And then with the straight line AC taken as common height, as AC is to GC, common height is the step where you always multiply the same thing on both sides. So I think I'm multiplying by AC on both sides. Okay, so I guess that checks out. And then similarly with BA taken as common height, as BA is to AF, square BA is equal to the rectangle AFBA. Multiplying BA on both sides checks out. And by elements 6, 4, as BA is to AF, AC is to GC. So I think that's just this side of this triangle to this side of this triangle is as, in this smaller triangle, the corresponding side BC is to the corresponding side GC. And the center C bisects BA so that BC is equal to AC. So, oh, I see, I'm substituting. So I wrote BC here, I'm going to just replace it with AC because they're equal. Brought down everything else. Therefore, by substitution, okay, it looks like I'm taking this, the same term as here, so I'm substituting it with this and bringing that down on one side. Then on the other side, I have ACGC, which is here, substituting it with this, bringing that down. And then alternately, that's just indicating that I'm doing alternando, so that just means that the middle two terms are swapped, and I swapped them. And since BA is bisected by the center C, square BA is equal to 4 square AC. This is, clearly I wrote this when I was a lot further through Apollonius than we currently are. But this is a step that Apollonius does sometimes where if you have a line that has a midpoint, so in this case ABC, then the square on AB is going to be 4 times the square on AC, just because the square on AC is AC times AC, and the square on AB is AC plus AC times AC plus AC. But you can just see this visually here, where this part is 1/4 of this whole square. So Apollonius does that, but I don't think we've gotten to it yet. But anyway, that works. Therefore, let's see. So I think what I did was, on this side we have as square BA is to square AC, this rectangle is to this rectangle. And we know that BA is sort of 1/4 of AC, so rectangle AF must be 1/4 of rectangle GCAC. So I just wrote that out, basically. And then by 113, it was shown that the square on DC, because DC is an ordinate, is equal to the rectangle GCAC, which is this part. And since DE is bisected by the center C, the square on DE is equal to 4 the square on DC. That's the same concept, just with the line DE instead of AB. The thing about if a line is bisected, the square on 1/2 of it is 1/4 of the square on the whole of it. And rectangle AFBA is equal to 4 rectangle GCAC above. I'm just rewriting that. So then by substitution, so I think we're starting with this step, which is why I wrote it out like we're starting with that step. And then we have 4 square DC is equal to the square DE. And we have 4 rectangle GCAC is equal to this rectangle. So I think that what I'm thinking is there's a missing step, much like Apollonius, there's a missing step, right? Where I multiplied both sides of this by 4, and then on one side I'm substituting that for the square on DE and bringing that down, and then on the other side I'm substituting this multiplication by 4 for this and bringing that down. But anyway, I guess that works, so and then taken in reverse means and extremes. DE is on the means, rectangle AFBA is on the extremes. So that makes it as BA is to DE, DE is to AF, which it was required to prove. Anyway, so that makes DE a mean proportional to the sides of the figure, which would be AF and BA. Now, I don't know if this proposition is really all that useful. I don't know that it needs to be proven necessarily. But anyway, I remember having kind of a lot of fun making this. I would kind of recommend trying something like this if you want to. I think, it's fun to read Apollonius as a way to learn his logic style, because I feel like his mathematical writing is pretty unique. I think what I did to make this was just write out, like, every possible thing that I would know about this figure, and then try to string together one piece of logic to the next. I think probably what I did, for example, was think if I'm trying to get to this ratio, you know, can I do means and extremes on this, and then how can I get to this result? So you can kind of try to work backwards from the result you want, and then try to see what other things you can find out about that result and see if you can connect it to what you started out with. I think reading Apollonius, especially the longer propositions, it kind of just seems like random fact after random fact with no like clear understanding of like what the path even is that you're on currently. And I think trying to construct some sort of bizarre path like that for yourself is kind of interesting. It makes it seem less like something some ancient guy did once, and more like something that a human being figured out. And that's what I like about Apollonius. So anyway, this is not really the most useful video, but I hope you liked it. I thought it was fun to make.